Hello, everyone. Today we are going to be graphing exponential growth and decay functions. As always, though, before we get started, if you want to give the Ignite at the top of the page a shot, please do so now. All right, final answers up. First step on this, remember if there's ever a square root involved with a variable underneath, the goal is to get the x out of the radical. So in this case, whenever you have a radical and with a variable underneath, we want to get it alone. Divide both sides by -3. Once you do that, then you can take care of canceling out that radical. The opposite of taking the root of something is squaring or cubing or raising it to that exponent. So opposite of square rooting is going to be squaring. So that's what we do to both sides. And then we just solve like normal, subtract by 4, divide by 2. You get your final answer of 16. Now, today, the main goal is obviously exponential growth, which is exponential decay. And the differences, obviously, between last unit and this unit is radicals don't follow the same kind of curve that exponential functions do. When we say that something is either growing or decaying exponentially, we're saying that it's changing rapidly. We're getting really large really fast, or we're getting really small really fast. And that's basically what, when we say growth down in the vocab section, when we say growth and decay, there's always what's called a rate. And it's predetermined usually for any given scenario. There is the occasional time where you have to figure out what it is. And those are some problems that we are going to work on solving. But we're in general, if we're talking about growth or decay, we're just saying that that rate is going to get really large really fast over time because that's what exponents do. If you take any number, let's say you take the number 4 and that's not one. If I take the number 4 and I raise it to a power, if I raise it to the second power, 4 times 4 is 16. If I keep going though, if I take 4 times 4 times 4, 4 times 4, 4 to the third, 4 to the fifth, 4 to the seventh, if I get larger and larger, your numbers that you get out get, like I said, really large, really fast. So when it gets really large, really fast, that's what we just call exponential growth. And decay, obviously, is when you get really small, really fast. And there's a lot of real life scenarios where these two cases kind of come into play, but they both are based on kind of the same equation. Y equals AB raised to the X. Now, the difference is if it's in your growth scenario, B is what we call that rate. So when you're in a growth scenario, an exponential growth, B is just always something that's larger than 1. So that's where if you're raising the number 2 to a power, 10 to a power, 20 to a power, your graph is going to change pretty drastically then if you make B smaller. And that's what happens with decay. For decay, basically, we're not going to go negative with B, so it's still going to be greater than 0, but we're going to say it's between 0 and 1. So some sort of fraction, 1/2, 1/3, 2/5, 7/9, something along those lines. That would be your typical, that's how you know when a function would be decay versus growth. So if you look down below, when all we're going to focus on today specifically is what does an exponential function look like? And kind of similarly to when we work with square roots, cube roots, roots in general, this one is a little bit of a twist on that, in that there actually is something called an asymptote with this. And we haven't really worked with asymptotes all that much. But asymptotes are basically just invisible lines that your graph can't cross. It's not just that it won't cross, it's that there's a limit somewhere in your function that will make it physically never able to cross that. So let's start off simple. We're going to start off with this guy right here, example number 1. And the first question we're going to answer is it growth or decay? And the simple answer to that is whatever number is being raised to the variable. All we're going to look at is that number, is it greater than 1 or is it in between 0 and 1? And ours is clearly greater than 1. So we are working with a growth function because B is greater than 1. Now, domain, range, asymptote, I'm going to hold off on that for a second until we actually go ahead and we get to actually start graphing this. So I'm going to share my calculator with you guys. So that's actually what we're going to do next. So we're going to type this into our calculator. I'm going to go to the y equals. I'm going to obviously clear all this out. And I'm going to type it in exactly as it looks. I'm going to take 2, and we're going to use the caret key to bring up a blank exponent. And we're going to type in, x into that spot. So if you hit graph, let's see what this looks like. And there we go. So you might have seen the graph of an exponential function before, but you probably never knew what the equation looked like. But this guy right here is exactly what we're going to go ahead and graph. Now, the picture is great. I usually like using the points to be a little more accurate. So I'm going to go second graph, and I'm going to look at the table. And honestly, I'm just going to pick I'm going to pick maybe, let's do like, I don't know, 3, 4 points. I'm not going to like look for anything specifically, but like -1, 0.5. I'm going to pick some that are relatively easy to graph. If you get smaller, you guys are going to notice that as x gets smaller, y gets really small really fast. Where it says e to the negative number, that basically just means your decimal point keeps moving to the left. So your numbers keep getting smaller. So I'm going to just graph some nice ones. So we have -1, 0.5. Let's graph 0, 1. That's a pretty nice one. 1, 2 is pretty nice. And let's end with 2, 4. So we're going to go back to my other screen. And those are the points that we're going to graph. There we go. Okay, so I'm going to put this on my graph right now. All right, now I just graphed the points. Now to fill in the rest of my graph. Now here's where, if you look on your calculator, it depends on what version you have, but it kind of is a little deceiving because it looks like your graph kind of stops there. But it doesn't. This kind of tail on the left-hand side, right in here, that doesn't stop there. What happens is, if we could draw it accurately, it gets closer and closer to that x-axis, but it never actually reaches it. And that's because of what the nature of exponents do. But this makes sense. If I raise 2 to the first power, well, 2 to the first power is 2. 2 to the second power is 4. When you raise something to a power, you never get 0. It just either gets really large if you pick a larger number, or it gets really small if you pick a really small fraction if you pick a smaller number. But it never actually reaches 0. So because of that, that's why we actually have an asymptote in this problem. And the asymptote is whatever axis or whatever line we get really close to on the bottom side. So that equation right there, if it's a horizontal line, that's just y equals, and it's at whatever value it crosses through. Now, in this case, it's my x-axis. It's not always going to be the x-axis. I'll do one in a sec where it's not. But what that does is it kind of limits some things. And it's really only going to limit our range. Exponential functions, our domain is always the same. It's always all reals. Because you can pick any x value and you can plug it in for the exponent. The only thing that, like I said, if you pick a negative number, it just is going to give you a fraction. And if you pick any whole number to plug in, it's going to turn out to be a number larger than 1. So any value you can pick, you can plug in anything you want for your x's. Range, on the other hand, you don't get all values out. You only get all values that are greater than 0, because you can never reach 0. So because of that, my range is going to be everything greater than 0. And it does not include 0. It's not greater than or equal to, because you literally never will get 0 as an answer. Now, if you look far enough on your calculator, eventually your calculator will give up and it'll start putting 0 there. But that's just because it doesn't have the computing capacity to be able to keep figuring out the smaller number. So just be aware when you graph those, this actually has a tail. Like down here, this actually just goes forever. It gets closer and closer to that x-axis, but it never crosses. So how about you guys give it a shot? I want you guys to try one on your own. Try example 2. Pause your video now and try it out. All right, so for this one, I showed the calculator first. Should be what you would have typed in. Just be really careful that there's 2 on the end. Make sure that that's not typed into the exponent. So remember, if you're in the exponent, you have to arrow to the right, down, out of it, and then you can clearly see what the graph is. Now this one, it kind of appears that I've shifted up a little bit. And you can tell that because if I go in my calculator and you look at my y values keep getting smaller until they approach what number? 2. Now again, this is where you have to realize your calculator is kind of lying to you because the answer, it doesn't actually reach 2. The reason that it says that is because that actually is what's in the equation. Remember, when you have a number added on the end, that's like a vertical shift. It's just moving my graph up 2. So what that does for us is that actually creates our new asymptote. Typically, it's obviously always usually at 0 unless it shifts anywhere. This number on the end here tells me that I shift up 2. So my asymptote, instead of being at 0, is now going to be at 2, which in turn, now, and the asymptote, this is where on the graph, we're going to represent this using a dashed line. You do need to show that as part of your graphs. But all I did was I then picked 3 other points, and now we can kind of fill in the rest of my graph. I'm going to go through and hit them as best as possible. And then on this side, we're going to continue that. We just want to make sure that on that left side of the graph, we don't actually cross the asymptote because it's not. And that also kind of changes our range. My graph never goes below y equals 2. So y is always greater than 2. And those should have been your answers. This was a typical growth because we had a b was always greater than 0. It was a 3 in this case. A typical decay one would look kind of like this problem right here. Decay is where you would have that b inside, which is a fraction. So on example 3, that is your typical decay function. So if you want to give these 2 a shot, Miss Hardy is going to go through 1 or 2 of these. But other than that, right now, then you can move on and you guys can start the homework for the day.